Alright, to begin with, we're going to look at a cylinder, and this is doing uncertainty analysis. Let's say someone were to measure the diameter and the length of a cylinder, wanted to know the volume of it. Typically, you would have a diameter equaling to, say, I don't know, 30 plus or minus 3%, and a length, say, 10 plus or minus, say, 4%. And if you're looking at that, that's going to be 30 plus or minus 0.03 times your 30, which is going to be 30 plus or minus 0.9, 10 plus or minus 0.04 times 10, which is equal to 10 plus or minus 0.4. Now, to determine the uncertainty associated with random errors, you would end up with the uncertainty associated with the volume equaling to the square root of the partial with respect to the diameter squared times the uncertainty in the diameter plus the partial of the volume with respect to the length squared and the uncertainty in the length squared. Now, this is a very, very simple problem, so I'm going to basically lay this out in MATLAB this way, and I could fill out the rest of this, but I'm going to go straight on to MATLAB now and bring it into view so we can see how we can use that using cells in MATLAB. So let's start by taking a look here at the menu item called cell. If you disable it, you don't have cell modes, but make sure cell mode is enabled and you'll have this menu bar right down here. Let's put in a markup text and let's do what's called a Latex Inline math. And what you see is it puts something in here. We're going to basically make use of this in a moment, but let's start by taking a look at our equation. First, we're going to turn things into symbolic variables, length and diameter. Now, if we want to run this, you'll see it running it in the command window. Hit this. I'll need to save it. So I'll save it as let's see, volume UN for volume uncertainty, and come back here and run it. Now, at first glance, you may see nothing there until you realize I'll bring over the workspace window, and what you see is a D and an L. You'll also see that it appears like the type is a SYM or symbolic, and it has a box right here. So all it did is create a symbolic variable there. Next, I want to basically write down V is equal to pi times D squared divided by 4 times length. And now when I look at that, it repeats itself. However, by executing this statement, it put a new variable in here. It created a new variable v that's symbolic as well. So what I'm going to do now is hit 2 parentheses. It will turn it into a new cell. Call it take differentials, and I can put a few other comments there. And I could say p partial of v over partial of d would equal to v with respect to the object d. Let's run this code, and if I typed it correctly, what you find out is it took the partial of this with respect to d, and of course that would end up with a end up with a 2 pi d over 4l. That would have crossed that out, so you get a pi, a d, a l over 2. Pi d l over 2. And at this point, I'm going to put in the uncertainty. I'm going to need to, okay, I'm running out of space. I'll make it capital UD is equal to 0.9. Uncertainty L is equal to 0.4, if I did that correct. Now when you run this code, you'll notice that these two are not symbolic. These are double precision. So those are of type double, and that's because they're numbers. These are all symbolics. And now my last thing I'm going to do is this. I'm going to figure out the uncertainty of the volume. And I'll say UV is equal to square root of, now I may stop and do one other thing here, and that is capital P V P D sorry about that, PV. Now what I'm trying to do is I'm trying to make this similar to that, except this is going to be the symbolic form. This is going to be a numerical form. And to do that, I'm going to use SUBS, substitute. So I'm going to substitute in, for this symbolic variable, 2 components. Now we've already seen that in this you end up with a D and an L. For D and L, I want to substitute in, what do I want to substitute in? For D, I want to substitute in 30, and for L, I want to substitute in 10. Now if you run this, unbalanced parentheses, let's see, oh yeah. Now you have to be aware that this symbol, these 4 symbols here, are the curly brackets. These are parentheses. So all of these are curly brackets. Left curly bracket, right, left, and right. These are actually cells put in here instead of arrays. So let's try this again. So the partial of V, the volume with respect to the diameter for the numbers I have is 471. So I can do this with the other one. P V partial L, substitute in for this symbolic equation the same set. You want to make sure you substitute in the same set. And now you want to go ahead and figure out the uncertainty in the volume. And it's nothing more than this squared times the uncertainty in D squared plus this squared times the uncertainty in L squared. So there's the uncertainty in V, the volume, that is. Does it seem reasonable? I don't know, but let's take a look at one thing. We need to have the actual volume in there. So let's say VOL is equal to, substitute in V, comma, and we're going to substitute those values in. Then we're going to print it out. All right, so there's a better way of doing this, but I'm not going to worry about that right off. So the actual answer here, from what I've gotten so far, is that the volume is 7,000 plus or minus 509. If you wanted to break it down, it's around 7% roughly. So ironically, what lended itself, if you think about it, it was plus or minus 3 and 4, ended up with a higher error. So now the question is why did I represent this in cells? First, let's look at, we're going to go back and take a look here. Let's try this. Now, if you look at this and run backwards, you'll see that he came up with something strange for this command, LATEX, latex. But if we take this now and do a copy and put it right here, let's try this. We'll go to this command right here. We're going to hit this button, save and publish, give it a second. Now what it did is it created a window. I'm going to drag that window back over. Now, if you take a look, it created blocks and outputs from those blocks. Here it created that, and it created that underneath it. Now, This is not a direct setup, but it says to the effect that pi, and it says dv, which I have no idea why I put that there, but if you want to correct that, we can correct that and take out that, run a new. Now what you see is pi d squared L over 4. And if you hover over it, you'll see the command for that. Now, what I discovered, I took a pause there for a minute, to put $2 will increase the size of this equation here. Alright, so we're sitting here taking a look at this, and what we've done is we've created a document, if you will, and the document has all the information here. Now, you can go back in and put a title on each section. Let's put the first title Symbolic Creation. We'll hit that once and you'll see something called Symbolic Creation. So the contents are right here. The next one is take differential, take the derivative of the equations, hit the publish. You'll see take derivative of the equations. So I do a symbolic creation. I could put in a cell that says determine the volume. So symbolic creation, determine the volume, and for that matter, now I no longer really need that. Uncertainty of the measurements. Substitute and then I'm going to put in one more. Determine uncertainty in the volume. And that's pretty much it. So just like that, I've created this document. Now, one of the things I want to do and continue to do is I want to continue this on. Now I'm going to do a new cell. My new cell is going to be using MATLAB. Force the. Okay, so here's what I'm going to do. I'm going to do another cell. Set up a numerical experiment. Okay, so first I'm going to go in and do this. I want to now go in and say diameter. So what I could do now is clear all the variables. And then I can say diameter is equal to 30 plus 0.9 times, or I may, well, that's good enough, 30 plus 0.09 times random normal distribution, say 100,000 experiments, and I can say the length is equal to 10 plus 0.04 times random normal 100,000 experiments. Let's see. Next thing I want to do is a histogram of D, putting out there, say, 50 locations there. Now, if I publish this, let's take a look at what happens when I publish this. Let's shorten it down. Go ahead and publish this. What you'll see is it creates the inline histogram here. Now, I can go in and say title, diameter. Then I can go down here and do a histogram on the length. And what you're going to find if I publish this, you go down here and you only find one histogram, and it's the one with the length on it. What has actually happened is it came in and executed this histogram, put the title on it, executed this statement, created a new histogram, and put the title on it, and saved the last plot. It only saves the last plot. So what you need to do is you need to go in right here and put a new cell so you can get both histograms in here. Okay, if I put a new cell in here, I'll call this one length data. If I'm going to do that, I might as well create something in there called diameter data. You hit that and it regenerates this. It generated the diameter histogram and the length histogram. If you don't like that and you want a few more points, put another 0, run it again by publishing it, and what you get is a nicer looking plot. You might not like that you did 50, so you might want to do, say, 90. Adjust it to the point where you like what it looks like. Now I can just go down and hit this and go. Now you start seeing a very smooth looking Gaussian plots. Now what I'm going to do, I'm just going to go in, go straight in, do the volume data. Volume is equal to pi times diameter period squared divided by, with a period in front of it, well, I don't really need to do that, but I can do a times the length divided by 4. I don't need to see everything, but I can go in here and hit this and put the volume in there. Hit the publish key or the publish button, and I get my volume out of here. Now, one of the things I needed to do along the way is, here's what I'm going to do. Mean, I'm going to look at the mean of the diameter. Or let's do it this way. Fprintf diameter equals to %f, and we'll just call it plus or minus %f, and a carriage return, and we're going to do the mean and then the STD of diameter. Close it out, and let's run that one case, and we'll look at the answer. What I get is 30 plus or minus about 0.9. That's about where I was. Do the same thing, so I'll just do a copy. Go down here under the title here, put a paste, but this time it's the length. Copy, paste. Looking at the length. Then I can copy, go down here and put it in here as the volume. And hit the publish. And I should have the whole thing. Now up here I get 7068 plus or minus 509. 7074 plus or minus 509 and change. So I'm getting about the same thing on both of these. What I see here is the distribution that comes out of the volume, and the distribution that goes in, and the other distribution that goes in. So there are two ways to solve this problem. Now, the next thing is you're going to have to write a report. So what we want to do is we want to find out where this at. Users, so you'll see this particular location here in your, now yours will look different, but I'm doing it on my own computer, so you're seeing this. Now, you can drag over a Windows, a Word document, hit an open, and go in search of that. Documents, MATLAB, HTML, open. And just like that, you've got the same thing. Everything's in place. What you see is the same thing. You can go up here now and put your name and everything else. You can actually do a control and jump to that section in the document. So you've just now created, and the nice feature here is you've been able to include equations here. You can go ahead and make them larger, although they don't look very good larger. You can do things with them. Have some unspelling, some spelling problems. But you can fix this up, put your own name on it, and submit it in a Word document. You can go in at this point, save as, and you can save it as a Word document, save it somewhere, and now I have a Word document. It's basically, I've just converted it. So with that, this is a way of going through this, and again, I'll just quickly go through here. All I've done, and the nice feature of the cells is it gives you very distinct stopping and starting locations. The symbolic, so this is the MATLAB code in the shaded area, and the response to this, there was no response. Determining the volume, the output from MATLAB was that. Taking the derivatives, the output from MATLAB was this. Uncertainty of the measurements, and you notice I didn't put a semicolon here, but I did there, so you only got one output. Substitution, so I substituted in for D and L these two values. I determined the uncertainty of the volume and get these numbers. Now I'm going to use MATLAB to force the case. What I mean by that is basically I'm going to force feed this. I clear out all the variables. There's nothing left. All these variables are gone. I create a million, in this particular case, I create a million randomly normal distributed variables with a mean at 30 and a standard deviation about 0.9. I create a mean of 10, standard deviation of 0.4, So luckily it gives me back what I put in. And then I put those in a set of equations and determine the volume, determine the mean and standard deviation of the volume, and I can look at the distribution. So with that, this lecture's done. What you should be able to do is do this and create this as a report and turn this in.